Hi, welcome. Thank you for having me at Q2B. And yes, today I wanted to talk to you about scaling control to 1,000 qubits and beyond, and what quantum machines is doing to help make this a reality. So the outline is as follows. I also don't have many slides. The idea is the following. We're going to present the challenge, the barrier, this quantum classical interface challenge that exists for all qubit modalities. Sometimes people tend to focus on solid-state qubits, but atom arrays and ion chains have similar barriers. And then I will discuss what we do for the solid-state qubits and what we do for the optically addressed qubits, and how we think we can help all qubit modalities scale to these numbers, thousands of qubits, which we perceive to be the midterm challenge, kind of. And then I'm going to end with 2 slides about, okay, say you have enough control for 1,000 qubits. You now probably have a few tens of thousands of degrees of freedom that you need to control, and what are you going to do about that? How are you going to find optimal drive and readout parameters for your 1,000 qubits? So let's see. So this is a cluster, maybe not the biggest we ever made, but a representative one. This is a cluster of our previous generation of controllers, and this is what's required today to drive a 25 qubit Quantware chip. Okay, I will show you the next generation in a few slides, and all this rack will fit into a single box. So this is kind of our offering, or part of our offering for solid-state qubits, controllers at room temperature and cryogenic equipment down the fridge. And the reason this scales has to scale is basically because of the no cloning theorem. Basically because you cannot clone a quantum state, and so quantum information cannot fan out. You can't drive a qubit and then have this qubit multiply itself and send data to 4 other qubits. That just doesn't work in quantum computing. And so every qubit needs now a channel associated with it. You can do a lot of multiplexing. I will show you cool examples in the next slide. But you still need to have a channel per qubit. And so if you want to do hundreds or thousands of qubits, you're going to have to need hundreds and thousands of channels, of drive channels and readout channels. There's no running away from that. So the control of quantum computers will have to scale together with the qubits, scales together with the qubits. You might have a nice prefactor if you're doing atom arrays, but you still scale with the number of qubits. And it's not only the room temperature electronics that needs to scale, it's everything on the channel path. It's amplifiers, interconnects, filters, cabling, resonators, multiplexing equipment. Everything from the SMA port all the way down to the qubit has to scale. 1,000x if you want 1,000 qubits. And so this today is a big barrier to scaling. When everybody was doing and still is doing 10 qubits, it's fine. You take off-the-shelf equipment, a few of them, and you have 50 channels to drive 10 qubits or so, or 20. Now we're starting to see people move away from small-scale POCs like that into QPUs, which are at least a few dozen qubits. Quantware already has at 64 qubits. Others are going above 100. And so this quantum classical interface challenge, I didn't give the name, is a big problem. So this is for solid-state qubits. What's happening in atoms and ions, in optically addressed qubits. So this is each spot here on the right is an atom. This is from the Lukin paper done together with the Quera group. And here on the left is a very recent result by Quantinium. These are ions on the left, and they can move. So you can multiplex. You gain at least an order of magnitude. You can have a single drive channel region, and you can move qubits in and out of it to read or to drive or read. And so yes, so you get an order of magnitude. The problem is that they can do 10,000. So these are not atoms. This is a picture from Hannes Bernien lab, a customer. These are just the traps. Okay, we're not there yet. We're not going to make 10,000 very soon, but we are going to make soon. There is kind of a consensus in the atom array community that 10,000 qubits is around 2 years away. There's no big roadblock preventing us from reaching that milestone. And so, yes, atom arrays and ions can leverage multiplexing quite nicely, but you still need hundreds of channels. And on top of that, these channels are more complicated. They are not coaxial cables anymore. They are laser beams. You need to deliver hundreds of individually modulated laser beams now to drive at least a subset of these atoms. And so this is a channel. So not only do you need many channels, and this quantum classical interface must scale, but also every qubit modality needs its own kind of channel. You have DC channels and high-frequency microwave channels and terahertz channels for optically addressed qubits in the form of lasers. So what do we do for solid state? So we have the latest, the new quantum orchestration platform, the OPX 1000. It's a platform based on these OPX 1000, which are composed of front-end modules. It's a modular system that you can switch, put whatever module that you need. It was launched a few months ago with a single kind of module, this baseband module, 2 gigasamples, 16-bit. I won't go into technical details too much. And a week ago, we've launched kind of the complementary module, which is a direct digital synthesis module up to 10 gigahertz. So now, basically, the large rack that you saw in the first slide can be replaced by a single box like this that has 64 channels of whatever you want, low baseband, high frequency, readout. You can mix and match. So now, and these things can, again, the highest density controller that is available today, a modular architecture. The software, of course, scales as well, and we're continuously scaling it. So you program code for 1 or 3 or 5 qubits. It looks very similar if you have hundreds. Any-to-any data sharing, accurate synchronization, all things that aren't so trivial to do at scale. And this platform is now under the process of being gradually scaled up to a cluster of 32 such OPX 1000, or about 2,500 channels, to which you can add even more. These are only kind of fast channels. Quantum Machine separates the low noise DC channels, which are on a separate cluster for power conditioning reasons. So it's even a low estimate. No one asked us to build such a thing yet, because this is kind of what you would need for around 1,000 qubits, solid state, and no one does that today. But we believe that in the mid-term future, 3-4 years, things like that might become a reality. Yeah, so this is for solid-state qubits. But what do we do about the optically addressed one? I have signals here that I can generate. This is great, but I don't have lasers. And so we have partnered with Quera to deliver an add-on to the OPX device, which is a photonic control unit, which at the heart of there is a silicon nitride photonic interconnected circuit that hosts up to 256 modulators. This works from 500, 400 nanometers up to 1500. You can choose your wavelength, you can choose the architecture, and then these modulators are each controlled by the OPX 1000. And so now we've basically extended the OPX 1000 from a few gigahertz up to hundreds of terahertz. You can think about this as an up converter. So you come in with a single fiber, it's split on chip, and out of the chip come 256 beams, which you can both steer in space, position on a 2D plane, and individually modulate with modulation bandwidths of 30 megahertz at least, and sufficient power. Each modulator can support more than 10 milliwatt. So this is our attempt to alleviate kind of the I/O challenge for optically addressed qubits. And so great, so we have the drive channels. The readout for atom arrays, for ions, is done with cameras. There's still work that we can do there. We already work with low latency cameras to do low latency feedback with such things. But in general, we have what we need, I think, to drive 10,000 qubits. We don't have the 10,000 qubits yet. There are other problems that are not ours, so laser power is still an issue, and so on. But on the control side, on the electronic side, I think we have what we need. Okay, so we have the channels, but now you have tens of degrees of freedom per qubit on average. So if you have 1,000 qubits, say you have 1,000 qubits, that typically means you're doing circuits that are at least 1,000 deep, right? Otherwise, it makes no sense. You cannot build entanglement on the whole QPU. So now you have 1,000 qubits with a circuit that is at least 1,000 deep, and you know, we've lost our naivety to think that processes in quantum computing are Markovian. Things are not necessarily non-correlated. They are typically very correlated. And so every gate now, every parameter all along your circuit is a parameter. It doesn't really work very well if you just parameterize gates and find optimal drive parameters. You need to parameterize the whole circuit. And so 1,000 qubits, 1,000 deep, that comes out to be tens of thousands of parameters. What do? You're going to sit a PhD student to scan these? That's not going to work. And so for that, we've partnered with NVIDIA, basically, to create a new product, which we call DGX Quantum, and which is basically a low latency interface to an NVIDIA server, a Grace Hopper server, the new generation of super chips from NVIDIA, which include a CPU and a GPU, 250,000 threads, 144 gigabyte of on-chip memory. And so there's this large chunk of memory on this chip, and the CPU and GPU can both access the same memory, and they have a data sharing of 900 gigabytes per second. And we now also write to this memory from the controller. So on our FPGA-based controller, we have also variables and waveform memory and integration weights and a bunch of data that is used to synthesize signals for qubits. And now we can send and receive this data from a high-end NVIDIA GPU with a round-trip latency of below 4 microseconds. So this is now our accelerator. The NVIDIA Grace Hopper server is now an external compute accelerator for the OPX 1000 cluster. And originally, kind of the original use case for that was to run quantum error correction decoders. But the general use is to extract entropy from the system. So if you need to extract this entropy intra-shot, you have to do fancy quantum error correction things, but you still need to run some quantum error correction decoder in real time. And so the Grace Hopper can do that. If you want to stabilize your QPU shot to shot, job to job, because parameters drift, nothing fancy in quantum, but the frequencies of your qubits drift, the inhomogeneity drifts, crosstalk, and so on, you can now have powerful reinforcement learning models that can be learned in real time with a high rate. So, and this is kind of going, this is kind of a large objective of quantum machines, and that is to make QA and our controller and the programs that you write for our controllers differentiable. So every parameter now, what does that mean? That every parameter, every waveform, every integration weight, every wait time, every parameter of your circuit can now be changed after compilation. So you compile a program, you put it on the FPGA, it runs and executes, and shot to shot, within microseconds, you can now update these waveforms, the parameters, the angles, the amplitudes, and everything is synthesized on the fly based on the new parameters. And the goal is to allow these changes to be done shot to shot. There were some very influential papers that came out end of last year that show that these reinforcement learning models, when they are paired with quantum, with QPUs, you can optimize these parameters faster if you have the ability to change parameters shot to shot. It's not so trivial to realize why. The kind of simplest thing that you can do is to change a policy, try a certain circuit, and then do process tomography on the whole thing. But that takes a long time. You can do something that is smarter than that. but that requires you to change these parameters shot to shot. So you still can now leverage QA, our high-level programming language, to design these policies in a way that is flexible and that you can change in real time. You write your Grace Hopper kernels in C++ or Python, and then they both run in parallel. You develop kernels in the form of a persistent kernel that always runs in the background, and you load your QA program on your controller, and then they exchange information with a round-trip latency of 4 microseconds. And so that opens up the ability for you to de-drift and to build the noise eaters and stabilize basically your QPU. And so this is what we see as a necessary component to scaling. It's not only delivering just numbers of channels, which is still, it is a challenge, but also being able to manage kind of the parameter space that comes along with that. And that's it. That's my talk. Thank you.
Thanks very much, Ramon. So we do have a couple of questions, so I'll start with the simple one. So what is the switching speed of the PCU?
The switching speed of the PCU?
Yes.
What do you mean by PCU? The power supply?
So if anyone, whoever asked this question, if you want to clarify maybe what you meant by it.
The power supply, I don't know, the switching power supply, no, I don't think that's the question.
Okay.
What's the switching speed of the PCU?
Maybe if anyone wants to clarify in the app or otherwise. In the meantime, can you detail the benefits of the Quantum Machines NVIDIA partnership for quantum error correction with reinforcement learning? So maybe reinforcement learning as opposed to some other method. So
reinforcement learning is one thing. Let's say reinforcement learning is something you would do before you even attempt to do quantum error correction. You need to have nominal qubits with a certain, below threshold. You need to have your fidelities low enough, good enough, so that you can even start hoping to get quantum error correction benefits. So that's kind of, say, stage one. And then we're now working on benchmarking different decoders. We're not a decoding company. We're just doing this so that we're sure that we're building the right hardware. We will also probably give away these decoders for free as software, as we've always done. Software was always free for us. And then, yes, and so what we're seeing now is that for reasonably sized surface codes, for example, D21, D23, several hundreds of qubits, we simulate a noise of fidelities of 1% or so, and we do 50 quantum error correction cycles, and then we feed all that into a decoder, and we get that the decoding happens within a few tens of microseconds on the Grace Hopper. Still, this is very preliminary. We might improve on that, but that's already fast enough. So we're saying a single quantum error correction round is 1 microsecond. So you do 50 of those, you have 50 rounds. It took you 50 microseconds. And now the decoding part takes you 20. So it's OK, you're not stepping over your toes. You can do another batch of 50, and you will be able to decode before it ends. So it looks like it holds water. Then if you have different kinds of qubits, atom arrays or ions with a different level of connectivity, everyone will have its own decoders, and they will have to research what works for them. The point is that DGX Quantum is now a much easier platform to do this research. You write C++, you run things on a GPU, on a CPU. You don't have to wait for to print an ASIC if you want to build decoders based on ASICs. It's an easy playground to develop on.